2.06. 2.06 gets into rational functions as a quotient, written like this. So if f of x equals p of x over q of x. All right, so when we have that, q of x cannot be 0, right? We cannot have a 0 on the bottom of the fraction. So q of x cannot be 0. And what we find out that is the graph of this can increase or decrease to infinity or negative infinity without bound. So what we're going to look at is being able to figure out what happens when we have rational functions that are like this. So let's look at, for example, I'm going to change this instead of x to the fourth. We're going to go 1 divided by x. Right, 1 divided by x. And what we see there is we have a vertical asymptote, right, at x equals 0. Because we know with x being the denominator, 0 cannot be the denominator because we can't divide by 0. But what happens as we approach that asymptote? Well, it depends. If we're approaching from the negative side, then we see that the function goes farther and farther towards negative infinity. It'll never touch the 0, but it'll get closer and closer and closer to x equals 0. And in the meantime, you can scroll out as far as you want to, and it will continue to get closer and closer. If I can get on it down there, that closest. Let me click on the graph. It gets closer and closer and closer to x equals 0. This graph exists down here, but it goes towards negative infinity. Now let me click on a point because it's too far down there. But what happens on the other side? So when we approach this vertical asymptote, right, as we approach x equals 0, if we're approaching from the negative side, it goes to negative infinity. But from the positive side, as we approach the asymptote from the positive side, it's going towards infinity. So what we see is the function itself acts differently depending on which way it approaches the vertical asymptote from. From the negative side, it approaches negative infinity. From the positive side, it approaches positive infinity and goes on continually. All right, so let's talk about finding. Well, first of all, let's just talk about the asymptote, right? When we have a vertical asymptote, it is a line that the graph will approach but never touch, right? We saw it getting closer and closer and closer. And on this side, it was also getting closer and there, closer like this. But we also have horizontal asymptotes. And we saw that it actually had a horizontal asymptote at y equals 0 because there's no way that 1 over x could equal 0. Right? There's no way we could actually equal 0 in that. We can get really, really close to it. If we make x a billion, 1 over a billion is really close to 0, but it's not 0. So this also had an asymptote that was a horizontal asymptote. So we're going to be talking about vertical asymptotes and horizontal asymptotes in this and ways to find those. So if we have a rational function of p of q and p of x and q of x over the top like that, where they don't have any common factors, right? No common factors, then we can find the vertical asymptotes, the zeros of q of x. So zeros of q of x is a vertical asymptote. Any of the zeros from the denominator would be a vertical asymptote. And as far as horizontal asymptotes, it can have multiple, and there's a way that we can figure that out. Let's look at if we have to get some more detail about our function. Let's say that our p of x is it has a coefficient of x to the n power plus a to the n minus 1 to the x to the n minus 1. I can continue on all the way down to a of 0. So at most, it's a power of n. It can have to the fifth power, to the fourth power, to the third power, all the way down to the constant. And if we talk about the denominator, we're going to use m, right? So it'd be the same thing. We'll use b for the coefficient, m minus 1, x, m minus 1, all the way down to b of 0. So if we talk about the power of the numerator being n, right, the greatest power in that polynomial, and m being here, this is going to tell us something about the horizontal asymptotes. All right, so let's talk about horizontal asymptotes. Horizontal asymptotes. All right, and this is what we know. If n is less than m, all right, so if the power of the top polynomial, p of x, is less than the power of the q of x, the denominator, then x axis is the horizontal asymptote, right? Y equals 0. We know the horizontal asymptote if the power of the denominator is greater than the power of the numerator, which we saw in 1 of x, right? Because the power of the top is to the power of 0. It's just 1. This is x to the power of 0. This is x to the first power. So the power of the bottom polynomial is greater than the power of the top polynomial. So that fell into this case. The x-axis is a horizontal asymptote of y equals 0, which we saw in our graph, because it did not ever touch the y this way, or the x-axis this way, or this way. Now, what happens if they're equal? If n equals m, maybe we've got an x over an x, or we've got an x to the third over an x to the third. Right? 4x to the third, 3x to the third, whatever it is. So if they are equal, then y equals a over b is the horizontal asymptote. Means, like on this, y equals 4/3, whatever they are, becomes that. If it's just no coefficients, then it's y equals 1, right? Because the coefficient's 1 over 1. So we just look at those coefficients, and that becomes the horizontal asymptote, a over b, whatever this first a over this one is. I guess a of n to b of m, whatever that first coefficient that goes with the largest power. And the third case is if n is greater than m. So this has a higher power than the denominator. So we've got x to the 5th over x squared, right? Something like that. Then there are none. There's no horizontal asymptote if we have this situation. For one thing, when you have this situation, that ends up, simplifying. When you simplify all that, you'll end up getting rid of the denominator. Right. So anytime we have the power of the numerator higher than the power of the denominator, there are none. So there's the 3 cases for the horizontal asymptote. Just looking at a quotient like this, when we have our polynomial as a quotient, where we have a top and a bottom, there's the 3 cases for a horizontal asymptote. All right. Remember, the vertical asymptote is the zeros of the denominator. Whatever the zeros of this will be our vertical asymptote. The horizontal asymptote has these 3 cases. So that's a pretty cool trick from there. And that is what 2.06 goes over. So when you go through that lesson, this may help you understand what it's telling us. 2.06 talks about discovering the asymptotes based on the algebra right there. All right, let's look at 2.07. So 2.07 talks about graphing rational functions then, when we have f of x is p of x over q of x, right? And this, like I said, the assignment on 2.07 is an evidence of learning thing, because you're going to have to put together a lot of information about it. And what doing in here is we're talking about graphing this but looking at it algebraically, we're not talking about pulling up Desmos and graphing it. Want you to be able to look at a polynomial that's in this form and give the y-intercept, give the x-intercepts, give the vertical asymptotes, the horizontal asymptotes, determining the behavior of the graph to the left and to the right of the x-intercept and the vertical asymptotes, to be able, basically, you're going to describe everything that a graph would have. All right. So, for example, if we have f of x equals 5 over x plus 1, right? So our y-intercept is when x equals 0, right? We know how to find a y-intercept. When x equals 0, that's going to be it. So 5 divided by 1, because 0 plus 1. So we know that the y-intercept is going to be 0, 5. The x-intercept, when this is equal to 0, right? When that's equal to 0. Well, it doesn't exist. There's no way this could ever equal 0. 5 over x plus 1. Even if that's 0, it's not going to equal 0. There's no way we can get this equal to 0, so there is none. Then we look at the vertical asymptote. Vertical asymptote, remember, said that is the zeros of the denominator. Well, when is that 0? That's when x equals -1. So that is a vertical asymptote for that graph. What about the horizontal asymptote? Horizontal asymptote. Well, in this case, the denominator has a higher power than the numerator. So the m is greater. N is greater. Because in this case, our m, where am I at? Right there. M is greater than n. So y equals 0. The x-axis is the horizontal asymptote. All right. So we can find all this information. So we could draw this graph, start drawing this graph right away with this information right here. So this is what 2.07 is looking at, is being able to pull all this information out just from having the function. There's going to be one other thing that we add in here. A slant asymptote, well, two other things, actually. We'll also talk about a slant asymptote. We can have those, right? A slant asymptote. Maybe it's not always a straight horizontal and vertical line. So in a rational function, when the numerator has a degree of exactly one more than the denominator. So if the numerator has a degree that's exactly one more than the denominator, let's make this 3x squared. Well, I'm just throwing this out there. I don't know that the one I'm building actually has much of any kind of slant asymptote, but anytime this is one greater than that, we can use long division and find the slant asymptote. So here, they actually have one in our examples that does work. When you do this, if you have x squared minus 4x plus 3, and it's over x plus 2, find the slant asymptote. Well, if we divide this, which we can use synthetic division, right? We can do synthetic division. What we will find out is it ends up being x minus 6 plus, and then there's a remainder of 15x plus 2s. So in that case, this is the slant asymptote. Let's look at that on the graph to see what it's talking about. Okay, we had x squared minus 4x plus 3. And all of that, so I put it all in parentheses, so it'll all be the numerator, is divided by x plus 2. Look at that graph. There's a slant asymptote. And let's see, we said is at x minus 6, y equals x minus 6. There, we see that as it gets closer to infinity, it gets closer and closer to that line, but it never hits that line, right? We also know that denominator, the zeros of the denominator, is a vertical asymptote. So x equals -2. So we have a vertical asymptote, and notice two sections of that graph, one towards infinity and one negative infinity. But this is a vertical and a slant asymptote. All right. So the other thing that we're going to talk about is a hole. Our graph can have a hole that if we don't pay attention algebraically, we may miss that. So holes, well, we know vertical asymptotes are found with the zeros of the denominator, right? But what happens, put our P of X over Q of X again. What happens if the zeros in the denominator, which is our vertical asymptotes, get canceled out when we put this in its lowest terms? So for example, if we have f of x equal x minus 1 over x squared plus x minus 2. All right, we know we can factor that to be x minus 1 over x minus 1 x plus 2. All right, that is what that factors into. And when you look at that, we say, okay, well, we know the vertical asymptotes, right, would be with the zeros, which would be 1 and negative 2. But what happens when this cancels out? Right? So actually, we also have an x minus 1 in the numerator. Well, what happens is there's a hole actually at x equals 1, and this is an actual vertical asymptote. Let's look at the graph of that, see what we're talking about. Okay, so on top of the denominator, we had x minus 1. And down here, I'm going to go ahead and just do it as x plus 2, x minus 1. Graph it with its factors. Okay, so when we see that, let's zoom in a little closer. It's easy to see the vertical asymptote at x equals negative 2, right? But according to what we thought before, there should be another one at x equals 1, but this says there's a hole. Well, we don't see anything, but if we click right there on x equals 1, if I can get, look at that, it's undefined. There is actually a hole in our graph right there. So if we were graphing that, we would need to put a hollow circle right there where x equals 1, because that is actually just a hole in the graph. A hole in the graph. It exists on both sides. See, we have a value for the function on either side of 1. But right there at 1, this graph is not defined. Undefined. So that's something else that we're noticing in here, is that whenever we have factors together like that, that the same factor is in the numerator as the denominator, we're going to have a hole in the graph. Interesting stuff. We're getting way deeper into this than we ever got before in our algebra classes. That is the primary overall look at these 3 lessons, 205, 206, 207. It's all about the asymptotes and the graphing and being able to tell everything about this graph before we ever pull up Desmos or ever get out a sheet of graph paper. Learning all about this ahead of time so that we can know exactly what the graph looks like without ever truly having to graph it. So go through these 3 lessons. They're not terribly long lessons. At least 207 is pretty short. 206, anyway, I will let you guys go. And that is the basics of it. If you got questions, hang around or come to class Thursday or email me. And otherwise, have a great week, guys.
Let's get out of here. Word to your multiples. Math, baby.